So welcome to Wollongong, the home of the University of Wollongong that houses the Intelligent Polymer Research Institute, as well as TRICEP. TRICEP, the Translational Research Initiative for Cellular Engineering and Printing. It's about some of the work in TRICEP that I want to talk to you today. That work involves a partnership, a collaboration with Venus Shell Systems, headed by Dr. Pia Winberg. Pia introduced us to the wonderful world of seaweed. Pia introduced us to the exquisite molecules that can be extracted from seaweed. And our particular interest is in the identification of those appropriate molecules, their purification and modification, and their use in tissue engineering and for therapeutics. Alginate is probably the most commonly used biomaterial or biomolecule extracted from seaweed. It's a polysaccharide composed of different sugar groups arranged in a different way to create a rather large molecule. The arrangement of those sugar groups, often referred to as M groups or G groups, very much determines the physical and biological properties of alginate. The overall length of the molecule or the size of the molecule also determines the physical and biological properties of alginate. Now, we have used alginate in a number of ways. Previously, others have used alginate to deliver islet cells for islet cell transplantation. In that procedure, the very precious donor islet cells are wrapped up in alginate beads before being transplanted into the recipient. Those islet cells and that transplantation is used to treat diabetes in a very effective way. One of the Achilles heels of that treatment is that those very precious cells are often lost either during the transplantation or immediately afterwards. So the encapsulation in alginate helps to circumvent those problems and alleviates them to some extent. Our particular work in that area is with Professor Toby Coates at the Royal Adelaide Hospital. Toby and his team approached us to develop a 3D printed scaffold that would better protect the islet cells during transplantation. So we use 3D printing with alginate as a key component of our 3D printing ink to create a scaffold that protects the islet cells. But more than that, we are also able to introduce endothelial progenitor cells, which promotes vascularization to help sustain the islets after transplantation, and also T regulatory cells that helps regulate the immune response, again improving the performance of the islets after transplantation. So alginate plays a critical role in that bioink for 3D printing to create structures for translation and translation and implantation of islet cells into donors. We've also used alginate to encapsulate myoblasts, and this is for muscle regeneration. This time those myoblasts are encapsulated in long lengths of alginate fibers, which provides an environment to promote the generation of muscle fibers and then muscle tissue. And those fibers not only provide the right biological and chemical environment for the myoblasts, but also the right structural environment to ensure that they align and mature into healthy muscle tissue. On the more fundamental front, we have used alginate as a critical component of a multi-component ink to print induced pluripotent stem cells. These 3D scaffolds containing induced pluripotent stem cells are used to create neural networks on the bench. So we use 3D printing with alginate as a key component of the ink in order to protect those induced pluripotent stem cells during printing, and then to create the right environment so that they differentiate into the right types of neurons. This brain on a bench project enables us to get insights into the development of debilitating diseases like epilepsy and schizophrenia. We have also used alginate as a critical component of controlled drug delivery systems. We have, for example, created and fabricated microparticles of alginate containing dexamethasone, an anti-inflammatory molecule. We have utilized those microparticle formulations as injectables in order to treat inflammation in the ear. More recently, we've been involved in developing localized drug delivery systems to treat pancreatic cancer. This again involves the use of alginate, and we use alginate to incorporate drugs, anti-cancer drugs, into that capsule that can be inserted near or into the pancreas. This effective localized drug delivery system is much more efficient than systemic delivery of those particular drugs. We've also created patches using 3D printing, patches that enable, again, the localized release of those anti-cancer drugs, and the engineering of that structure of the patch can make sure that we can actually deliver efficient and pre-engineered release profiles for those drugs. So alginate is proven to be an amazing molecule in terms of cellular therapies, in terms of tissue engineering, and in terms of release of drugs in order to treat a range of medical conditions. I'd also like to talk to you about the work we're doing with another class of molecules from seaweed, ulvans. Ulvans are extracted from green seaweed, and again they are a polysaccharide, a large molecule built comprising of a number of different sugar blocks within that. And again, the arrangement of those sugars and the size of the overall molecule very much determines the physical as well as the biological properties of the ulvans. As with the alginates, there are many ways we can fabricate structures containing ulvan, and many ways we can use those special molecules for therapeutics and for tissue engineering. Ulvans are not so readily cross-linked as the alginates, which are simply cross-linked using ionic cross-linking, for example, introducing calcium. With the ulvans, we have chosen to modify the ulvan to attach methacrylate groups to that polymer backbone, and those methacrylate groups can be cross-linked using light irradiation. Those gels are very useful gels, high water content that we can create through light-induced cross-linking, excellent mechanical properties, and very high cellular compatibility, particularly with human dermal fibroblasts. We've also introduced ulvan as a mix, or as an additive to a mix of different components in different bioinks. We have, for example, introduced ulvan into a methacrylated gelatin-based bioink, again for the purpose of trying to accelerate or support wound healing. Here we find that we can again create the gels, but we get a double advantage of introducing the ulvan. Not only does it improve the biological or control the biological activity of that host gel, but it actually helps to support and to improve the mechanical properties. That's quite unusual. Often we're compromising biological properties or compromising mechanical properties. And here we have a molecule that can help improve both. So what we found is that the introduction of ulvan into those methacrylated gelatin gels improves the biological activity, regulating collagen production and also importantly elastin production, critical to control those during wound healing, and improves the mechanical properties of the overall structure. A final fascinating example of the use of ulvan is the incorporation of ulvan into a synthetic polymer. And that synthetic polymer is actually an organic conductor. It conducts electricity. And we found that we can effectively integrate ulvan with that synthetic polymer to create a structure that's electrically conducting and highly biologically active. In fact, we've been able to grow nerve cells on that structure, and we've been able to show that through electrical stimulation we can promote the growth of those nerve cells and promote neurite outgrowth on that platform. So again, ulvan presents us with many opportunities, just as alginate does in terms of tissue engineering and their use in developing new therapeutic approaches for medical challenges. But how are we going to see the wide deployment of molecules like this from seaweed into the clinic? It is challenging. It is challenging. I've already mentioned that some of the elegant properties of both ulvan and alginate come from that exquisite arrangement of the sugar molecules within that large structure and from the overall size of that large structure or that large molecule. So we have to be able to control those. We have to be able to reproduce that if we are going to get the same physical and biological activity every time we extract those molecules and introduce them into a formulation. That's going to require careful control over the farming and harvesting of the seaweed, careful control over the extraction and modification of those molecules, and then of course the development of appropriate sterilization methods, packaging methods, and deployment methods that see them into the clinic. We have all the steps in place in order to help us to do that. The partnership between TriCep and Venus Shell Systems covers that pipeline of activities, covers everything from the farming to the deployment of the molecules in an appropriate formulation. We are confident that partnership will deliver real clinical solutions using molecules from seaweed in the very near future. We look forward to working with many more of you in the seaweed community as we progress our activities. We are, of course, grateful to Dr. Pia Winberg for introducing us to the magical world of seaweed, to introducing us to the magical world of these amazing molecules that come from seaweed. And we're also grateful to the clinicians we work with in deploying these molecules into clinical formulations, that being, for example, Professor Toby Coates for the islet cell transplantation and Professor Fiona Wood for the wound healing and skin regeneration. If you would like to have more information about our activities in this area, please go to tricep.com.au and have a look at the partnerships that we're forming in the clinical world and in the seaweed farming world in order to deliver these solutions. Thank you.